everybody. It's a pleasure to be here today on the Rollup. My name is Alex Pruden, and I'm going to be talking a little bit about the economics of zk today, and in particular, the economics of zkRollups, since I think this is a relevant question for everyone interested in scaling blockchains. I know a lot of folks are really excited about zero-knowledge cryptography. I personally work at a project called Aleo, which is a zk layer one that's doing smart contracts in a privacy-preserving manner, using zk as well. So zk is a really popular topic these days, but I think the economics of it, a lot of people kind of focus on the cryptography and the moon math and the magic, which I think is all very interesting personally. But I think, for this technology to be relevant, of course, it needs to solve an economic problem, or at least we have to consider the economics of it. So that's what this talk is going to be about today. Hopefully this is enlightening for everybody. Again, I'm Alex. I'm the CEO of a project called Aleo. But before Aleo, I worked at A16Z Crypto. I was one of the first partners on the crypto fund there. And in general, I've considered myself a member of the crypto community since I got interested in the space in 2016 when I was still in the Army working in the Middle East. And I really was interested in zk in particular because I think it holds a lot of promise for solving real world problems, not only in Web3 but beyond, which is why I ended up at Aleo. So I guess maybe just some more context for this talk in terms of my background in zk. So I run a zk layer one. I run a group called the zk Study Club with Anna Rose, who is the host of the zk podcast. In that study club, we talk to a lot of zk researchers about the newest, latest, and greatest moon math. So that's what I do there. And then in addition to that, I run an initiative called zPrize, which is an open public initiative around accelerating zero-knowledge cryptography through hardware acceleration in particular. So I am thankful to have gotten a lot of experience in the space over the last couple of years, thankful to have worked directly with many of the leading cryptographers here. So I have a pretty in-depth understanding of how things work under the hood. And hopefully, the goal of this talk is to, again, talk about something a little bit less cryptography-like, but more, my master's was in business. I'm not a cryptography master's, but, I had more of like a business. I went to get an MBA. So this is more about kind of the economics we consider like building a business and using these for real world use cases. So, okay, I'm going to just go ahead and jump into it. Okay, so here's our agenda. I think it's important to start out by talking about, so we're talking about zk, but this is the roll up. And I think there's a lot of folks, including myself, who work in blockchain, with blockchain technology, and with cryptocurrencies. So I think it's important just to start off with defining what this is, mainly so we can get on the same page for comparisons later on. Because zkRollups in particular, or zk-scaling solutions generally, often are, kind of set in the context of a layer one blockchain upon which they are adding scalability, right? Or some feature, right? So I think it's important to just kind of understand, first off, or acknowledge what makes blockchains different than like like a ledger that a bank maintains, or a programming environment that I can access through like an AWS server, right? To be clear, there are plenty of applications for zk in those contexts, but they're very different, and the assumptions underlying them are very different than what we consider for blockchain. So I think that's what we're going to talk about first. The second is just kind of talking about what is zero-knowledge cryptography. Again, I just told you I have an MBA. I've been working with a lot of zk cryptographers for a while, so I'm pretty sure I can give a pretty satisfactory answer from a technical level. But for the purposes of this talk, we're not going to technically get into what zk cryptography is and how it works, or polynomial commitments, or any of that. We're just going to talk about it at a very high level, in particular around the interacting parties and the costs associated with both the proving side and the verifying side. And that leads us directly into the economics of zk rollups, right? Since we have to account for those costs, right? And those costs are part of this broader economic system, right? Which we can then look to understand like where the constraints will be and how do we expand that bottleneck, right? Lastly, we're going to compare the L2 and the L1 in terms of the actual costs denominated in a number of different dimensions. And we'll kind of just decide, maybe just leave as an open question, this approach and kind of where to go from here. So I guess maybe the last thing I'll just jump in. I'll just jump right into it. That's enough front matter. Okay, so what is a blockchain? A blockchain, as I define it, is a network of distributed nodes which process client transactions trustlessly. So what are the key properties? Again, I just said one of them, trustlessness. So I can operate a node. I don't have to count on whoever else is operating nodes to follow the rules. Why do I not have to count on any individual to follow the rules? Well, that's because collectively, via the process of consensus, in Bitcoin's case, proof of work, and Ethereum's case, proof of stake, in Aleo, the blockchain I work on's case, it's a variant of proof of stake called Narwhal Bullshark. we all collectively run this algorithm, and we know that if anyone is doing something malicious or misbehaving in some way, that collectively the broader group will kind of excommunicate them or punish them somehow in the case of slashing, right? So there's like an incentive to follow the rules. That doesn't mean that rules can't be broken. It just means there's a strong incentive to follow the rules. So that's why I don't have to really worry about whether or not everyone is following the rules, because I assume there's some collective punishment or collective incentive for everyone to do so. So the implication of that is that everything is trustless. The second implication is, as a client, I can interact with the network permissionlessly, right? If I'm a client, if I'm running a MetaMask wallet, let's say, I'm the client effectively, and there's a node out there that's a server. And if the node says, hey, I don't like Alex, he's a jerk, I don't want to process his transaction, I can just go to another node and submit my transaction. Maybe it's my mom who runs this other node, and my mom's like, oh, I love Alex, he's a nice guy. I raised him, and I have a vested interest in processing his transaction, right? So the point is that as a client, I can't just be blocked from processing a transaction by a single party. Unlike, and again, it's like, maybe this is like a hammer over the head, but I guess like it's just important to call out that this is very different than like the banking system, right? Where they're like, okay, hey, I don't like Alex. I decided Alex is no longer allowed to have an account at my bank. Alex is now locked out of his account. There's really no way to get it back unless I convince that person who's the gatekeeper to give me permission. So this is what blockchains are really, why they're special, right? And I think it's just important to keep this in the back of our head as we're discussing the added assumptions that we bake in here when it comes to rollups, right? And other scaling solutions. Okay, so in order to like contextualize zkRollups a little bit, let's talk about what zero knowledge cryptography is for the purposes of this talk. Again, I promised a very high level elementary school overview, and this is what you're gonna get. Okay, zk cryptography discusses a prover and a verifier. There's these two parties, right? A prover wants to make a claim about a statement's truth to a verifier, right? So it's like, I claim X is true. And the verifier either accepts that it's true or rejects, right? And the whole magic of zero knowledge cryptography is that the prover is basically able to do this without revealing to the verifier anything about the statement being proven. That is, strictly speaking, the definition of zero knowledge, which is the last bullet that I highlighted down there. There's two other properties that we care about, which are kind of basically implied in any real world zk system that's used in practice today. But just to, for completeness of this talk, I'll run through them. Every interaction between a prover and a verifier is supposed to be sound, which is to say that the verifier should not accept, should not accept there's two accepts, should not accept a false statement, except with the EX version of accept with negligible probability. Just ignore the negligible probability part. That's what cryptographers say when they mean like statistically speaking, it's impossible, right? So verifiers, statistically speaking, will never admit a false proof, right? So you can never convince the verifier under a proper zero knowledge scheme that a statement is true when it is in fact false. Next, the statement is complete, which is to say that the prover can, like any one of a class of statements, like any string in a language. That's actually too complicated. I promised elementary school. Any statement in a family of statements, in the complete family of all possible statements, can be proven, right? So it's really about saying that the prover is unconstrained. They can prove whatever they want within this giant context, right? Okay, so that's what zero knowledge cryptography is. Now, I think the main reason I wanted to pull up the slide is, again, just to highlight the fact that there are two pieces here. There's a prover and there is a verifier, right? There's not like a prover doesn't exist in isolation, a verifier doesn't exist in isolation. A zero knowledge system inherently contains these two parts, and it's both of these parts that we have to analyze when considering the economics of a zk rollup. Okay. Okay, cool. And then I think it's, by the way, the definition I just gave you is from a 1980s paper, right? 1982 paper, the GMR paper, which, these were basically invented. Of course, zk has come a long way since 1982. I probably don't have to convince any of you that. But the idea here is the main innovation that has come since is that there's this concept of a succinct proof, right? And this is actually, for those of you who want to know what zk-SNARK stands for, zk-SNARK actually stands for zero knowledge succinct argument of knowledge, right? And this succinct here is doing a lot of work. Typically, it means either the proof is small relative to the whole statement being proven, or it means that the time for the verifier to check the proof is short relative to the time it took the prover to communicate that whole proof to the verifier, right? These are kind of fuzzy in terms of like their strict definitions, and this fuzziness is what permits basically this entire galaxy of different zero knowledge proofs constructions. Snarks, as we typically refer to them in blockchains, are really referring to a specific category of zero knowledge proofs of ZK snarks that use polynomial commitment schemes. And, I'm not going to like go and disambiguate or get too deep in the weeds there, but the long story short is snarks, as we typically refer to them in blockchains, use these polynomial commitment schemes as a key building block. And the nice feature about them is succinct in this case for the ZK snarks. And by the way, let me define like where you would see these. This is like ZK snarks as in used in Zcash first and foremost. I mean, they were really the pioneer for ZK proofs in blockchains. And then, later constructions like we have Aztec, we have Tornado Cash, several of the Rollups, the ZK Stink uses a vanilla, we'll call it snark approach, right? And succinctness defined in this vanilla snark here, you can actually see, for those of you who aren't familiar with computational or algorithmic complexity terminology, this O parentheses terminology is really about how a value scales, as you increase the n, right? So let me try and not make a self-referential definition, right? So here we have algorithmic prover complexity. So you have O of n log n. So if n is the size of the statement being proven, the scale at which that the proof time grows is basically the factor n times log of n, right? So that's kind of how people, computer scientists talk about how things scale up. So you can mostly just ignore everything I just said if you're not interested. The point is that the traditional flavors of ZK snarks that we see mostly in blockchains use this special type of commitment scheme, which means O of 1 complexity for the verifier and O of 1 proof size, right? What does that mean in human terms? That means that no matter how gigantic the statement is that I give you as a verifier, using this scheme, that proof is always the same size. I mean, literally the transcript could be the size of the galaxy, like you could take up that much paper, but the proof, like the statement being proven could be that big, but the proof is always going to be the same size no matter what, right? So that's a really nice feature, right, in terms of size, right? And then the second is, no matter how giant that proof, it will take the same amount of time for the verifier to check it, right? So no matter how big it gets, the verifier time and the proof size is always constant, right? So we're talking about the economics of rollups and the economics of proofs generally. We have to remember that there's economics implies like a dollar or a currency, there's some kind of like economic or financial value, but the economics can also be defined in terms of computation, right? And that computation can be broken down into memory consumption and actual computation, as well as storage, right? And why would storage matter? Well, storage matters particularly in the context of blockchains, back to how we first defined it, right? Because if a blockchain node operator has to store 4 million terabytes of storage, I don't even know what that would be, exabyte or something, I think, right? Like that's obviously that's not within reach of the average person, right? My laptop has a few terabytes, so it's not running an exabyte large blockchain, right? Which means now that there's basically a gatekeeper in the center of this whole thing, right? So that's why we care about size, right? Okay, so I kind of talked about the first column a little bit. If you ever see this terminology over on this, I think the sixth line down, this Groth 16. This is kind of the most vanilla of the vanilla version of snarks. This was pioneered by Zcash, and Groth 16 is kind of like is what a lot of people refer to when they talk about these like early types of snarks. Although Plonk and Marlin, two other proof systems that update Groth 16, which allow for universal computation instead of a single statement, are in this family as well. Okay, in the interest of moving on, we could probably come back to this slide during Q&A, but I want to make sure we keep moving here. But there's also Starks, right? So many people have heard of Starks, mainly because of the company named Starkware, which the authors of the paper which describes Starks, which stand for Scalable, Transparent Arguments of Knowledge, so ZK Stark stands for Zero Knowledge, Scalable, Transparent Argument of Knowledge. So if you notice, there's actually a little bit of a difference. In ZK Snarks, the S stood for succinct. In ZK Starks, the S stands for scalable. Again, it's a slightly fuzzier definition, but you can kind of see why over here, right? So what's the advantage of a ZK Snark? I'm not going to explain the difference between log and polylog, but the short answer is, generally speaking, Stark proving is faster. So Starks you can use to prove a statement faster than you would the equivalent statement with just a vanilla or Groth 16 style snark, right? That's the advantage. Now, why is this called scalable instead of succinct? Well, because compared to the vanilla family of snarks, Starks actually do not have a constant time verifier or a constant time or a constant size proof, right? And you can actually see in practice the size estimate for a transaction here. You can see this is a single transaction compared to the single transaction. Just ignore the proving key because that sits on the client side. We can ignore that for the moment. But the single transaction size is 200 bytes for a regular zk snark, and it's 45 kilobytes for a zk stark, right? So, and that, by the way, scales up. As you can see, like here, these two numbers are the same. Here, these two numbers are, one is much larger than the other. That scales up, albeit logarithmically, but it scales up the more transactions you kind of pack, or the bigger the statement gets, basically, right? And in addition, the verifier time is also not constant, right? So the verifier time takes a little bit longer, and it scales up as the statement grows, right? Now, what's the advantage of this scheme? Well, again, it's slightly faster prover. It also doesn't require what's called a trusted setup, which is a whole other probably topic for another day. In short, I think trusted setups are a little bit overemphasized in terms of a potential vulnerability. And this chart I pulled from a great repo, by the way, for anyone who's on GitHub. Awesome zero knowledge, maintained by the Matter Labs team. Great resource. That's where I pulled this chart from. Okay, but moving on here. Okay, so now we kind of have an understanding of like how this works. And okay, so now what's a zkRollup? I meant to put it in the slide here about what defining a zkRollup is, but maybe let me just verbally describe what a rollup is. Okay, so in Ethereum, we have basically the world and the history of the world separated into blocks, right? And each block represents a 15-second time interval, right? And inside that 15-second time interval, different things can happen. Then the way that things happen is via users sending transactions. I send someone some USDC, someone else interacts with Uniswap, someone's trading some NFTs. So these are called state transitions, and these state transitions are affected by transactions, right? Now, what's the problem with this? Well, the entire Ethereum network has to re-execute every single one of these transactions, right? So because the Ethereum network is executing every single one of these transactions, you can see how pretty quickly you hit a scalability bottleneck. And so anyone who's lived through like 2017 or 2020 times when crypto is like really happening, the gas costs in Ethereum just absolutely launched through the roof, right? And that's partially because of this fact that everyone is re-executing all the same transactions. And, and therefore the scalability is constrained. Okay, so rollups were proposed as a solution to this problem by offloading some of the off-chain computation, right? It still requires that. So maybe before I talk about the requirements, let me just talk about how it works. So a rollup is basically a separate, system, if you will, in which I, as a client, can delegate basically the execution of my transaction, not to the network of all the nodes in the L1, but to maybe a small subset of those nodes, or a separate set of nodes altogether, right? And then the idea is that maybe this set of nodes is using some faster hardware, or maybe there's like some other assumptions there. And then they basically settle that they do all this computation, and then they just post the result of that computation back to the L1, right? Now, as kind of initially described, the advantage of this was that you as the client were able to get all of the trustlessness and permissionlessness properties of the L1 by virtue of the fact that like every single block, like the off-chain network had to basically settle and prove all of your transactions that were happening off-chain. However, this is where we're going to get into the economics. It turns out that doing that is actually quite economically challenging, or let me state it another way. It's not economical, right? So and we'll talk about that now, right? Because the reality is the off-chain network to settle these transactions to Ethereum in the zkRollup case. So I'm only going to be talking about zkRollups now, which basically describe a situation or a system in which the proof that the off-chain network processed your computation correctly is a zero knowledge proof, right? So it's one of these. In the case of like zkSync, it's a zk snark. In the case of Starkware, it's a zk stark, right? It's a proof that, hey, we're at this off-chain, either one computer or a network of computers, processed your transaction, and now here's the result along with the proof that we did it correctly, right? And so there's a lot of advantages for a zk rollup over something like an optimistic rollup, particularly around you don't have to like go back and spot check whoever did the rollup. You can basically just trust by virtue of the fact that you can verify the proof yourself that everything was produced correctly. But what does that imply in terms of the economic costs? There's really two costs here, right? Because I said two things, right? One is that there's data that's posted about your transaction that gets put back on the Ethereum mainnet. That data is usually put inside of the call data section of a block, which this isn't a lecture about the structure of Ethereum blocks and how that works. There's a lot of great resources out there, but the TLDR is call data is kind of like, it's like the cheap it's just like some cheap storage bins you buy at Walmart, right? Like it's not really concerning like application state on Ethereum. It's just kind of there for extra stuff, right? And so basically the reason why rollups use call data is because call data per byte is cheaper than putting data into storage on Ethereum, right? So if you put it in call data, it's different than putting it into storage and it's cheaper, right? But nonetheless, these costs exist every single time there's a state transition on the L2. The L2 operator has to post that data onto the L1 in the call data in the clear, which is maybe like an interesting diversion or, kind of stepping back here. This is actually one of the reasons why I think it's a bit of a misnomer to refer to zero knowledge rollups as zero knowledge rollups, is because what we're really getting from the zk rollup is the succinctness property, right? So going to this slide. So you're basically batching a bunch of transactions into a single small proof in the case of a zk snark or even a stark, right? And so you're taking advantage of the fact that like it's only constant size or grows very slowly, but it's actually because of the fact you need to post all the information about each transaction in the call data in the clear, the before and after states. It actually doesn't give you privacy, which is another way of saying zero knowledge. Again, the academic definition of zero knowledge is the verifier learns nothing about the statement being proven other than it's true, right? So that's like just kind of like a little side note there. So call data posting is one cost, right? The second cost is proof verification, right? So Ethereum, the unit of account on Ethereum is Ether. What is Ether for? Well, Ether's there if you want to access the resources of that network, right? And the resources being the collective computational and memory and storage resources of all the computers around the world that are running this consensus protocol, right? And so all, like I said earlier, the reason why Ethereum was kind of running into scalability properties at these various times is because, or scalability challenges at various times is because, all of these different computers are having to like step through each state transition and then come to consensus one step at a time about the result, right? So if it sounds kind of like a lot of overhead, that's because it is. But, zkRollups let you get around the actual state transitions, but what they don't let you get around is the proof verification. Now, again, I said this is not going to be a lecture about zk, but all I'm going to say about zk in the context of the EVM, the Ethereum virtual machine, is that the EVM is a very general purpose world computer, as it is often called. And, world computers operate like in binary machine code. There's like EVM bytecode, which is kind of, you can kind of get a sense for like how things work at a low level on Ethereum by just inspecting the bytecode on Block Explorer like Etherscan. But the TLDR is like, it's just defined to be a very general purpose global world computer processor, right? Whereas zk and zkRollups are kind of defined over these very specific cryptographic settings, right? Which requires emulating that setting inside of this general computer. And if you don't understand any of that, it's not important. The point is that it's expensive, right? The cryptography that is needed to use some of these like performance zero knowledge systems is typically not supported in Ethereum directly, right? Okay, so that means that like proof verification is on average very expensive. Okay, and now here's the point, right? The point is that today in the real world, it's actually not the proving time that is the bottleneck for settlement on the L1. It's the verification cost, right? And it's exactly because of this slide, right? The proof verification in the case of Starkware, for example, it's 5 million gas. Keep in mind, like an entire Ethereum block takes 30 million gas as the gas limit, which means a single transaction taking 5 million gas implies that 1/6 of all of the operations of the world computer in that 15-second time interval are occupied with just this single transaction, which is the proof verification itself, right? So gas, of course, as I started explaining a second ago, Ethereum, the native unit of account ETH, the native unit account on the Ethereum network, is used to pay those gas fees, right? So they're very expensive, right? In the case of Starknet, these are this data is from September, I believe, of this year. I pulled this all from Etherscan as well as Dune Analytics, a great analytics tool for for analyzing Ethereum and other blockchains. But yeah, so the point is this, right? So Starknet, if to settle a Starknet proof on the Ethereum L1 is $75 in September prices average, right? So what does that imply? That means you need $75 worth of transactions on the L2 to make it worth it for Starknet to post back to the L1. In fact, the number is actually more, right? Because of what I said here. Because not only are you doing the proof verification, you're also posting all the call data for everyone doing transactions. And that you have to do every single block. And even though it's much cheaper, those costs can add up a lot too, right? So the TLDR is like the actual cost per proof verification is very high, even for other blockchains that don't use Starks. And the ZK Sync proof system uses a little less gas than Starknet, but as you can see, it's still pretty significant. But the upshot here is that because of this expense, it means that Starknet and zk Sync and all rollups basically have this property where they don't settle immediately. So keep in mind, back to the comparison with the L1s, you have this L1 on Ethereum, which maybe is pretty, blocks are full, lots of people are trading NFTs or whatever. And to settle immediately, you have to pay a high cost, right? But in the zk rollup world, there's really no way for you to necessarily force settlement immediately, right? Or at least it's not economic for the provider to do so in the long term, right? Because at the end of the day, every time they settle effectively costs this amount of money, right? And that's the first chart. The second chart is like, okay, on average, they get enough in fees to settle in this time interval, right? And so what effectively you end up having then, because of this fact, which is that verification is more the bottleneck than proving, you effectively have this case now where like you can either pay a lot for your transaction to be settled now on the Ethereum L1, or you can pay less, but you have to wait for it to be settled later, right? So I think this is one of the interesting, these economic implications of zk rollups that a lot of people aren't aware of. And this has nothing to do with hardware acceleration. You could accelerate, you could literally build a Dyson sphere around the sun and put all the GPUs in the world around generating faster proof. It still won't change this economics right here, right? The only thing that changes this is the cost of gas on Ethereum, and if someone invents an entirely new proof system that we're no longer aware of, right? Or that we're not currently aware of. Okay, so in addition to this reality, there's also kind of a reality of what is a zk rollup in a system in light of these economic realities in comparison to an L1 blockchain. So if I look back to this chart, I can send a transaction on L1, right? The dream of a rollup is that anyone can just be a prover, send the proof themselves to the L1 blockchain and settle their transaction immediately. The reality is that every single one of the zk EVM teams, every single one of the zk rollup teams on Ethereum all run a centralized prover, right? Which means there's an AWS, I'm assuming AWS or DigitalOcean or GCP instance somewhere with a gigantic CPU, bunch of memory, and maybe some GPUs or FPGAs that process your transaction for you. Back to what is an L1, and L1 is permissionless. This is no longer permissionless now, right? Sequencers, lots of ink has been spilled over how sequencers on rollups are going to be decentralized. I'm not going to comment on that because it's outside of the context of this talk. It's just to say that today, you rely on a third party for sequencing just like you do on provers, right? Similarly, the point of this talk has mainly been to point out the bottom two, or the third and fourth bullet, which is that proofs in the dream scenario are kind of really small and they're cheap to verify in gas terms, which means you can throw them on the Ethereum main chain all the time and basically just batch things very cheaply. The reality is they're not cheap, they're large, right? And the more people that use the L2, the more call data you have to post, which makes it very expensive for the operators, right? That's why you have settlement times that are much slower. So effectively a block time for Starknet in terms of settlement is 7 hours, right? Of course, it takes maybe seconds to execute the transaction, but to settle it on the L1 takes hours, right? And that's slow even when compared to Ethereum or even Bitcoin, right? And then lastly, I'm not going to touch on this either because it's really outside of the scope of this talk, but it is probably worth pointing out that these zk rollup constructions that let you emulate the ability of the EVM to do general smart contracts typically have to make compromises around the programming model because many of the underlying opcodes of Ethereum or precompiles don't exist to make a lot of these operations efficient, right? So in short, the compatibility with the EVM is limited at best. Cool. Further reading. I'll maybe post some links here, or I'll give the hosts of the show here some links that they can post. And maybe that concludes my talk, and we can take questions. Thank you all very much for your attention.
Awesome, Alex. That was a doozy. Thanks for the presentation, man. And yeah, I've got a couple questions. I think to start, maybe we could go to the types of zk proofs, and we could clarify the difference between the succinctness of snarks and the scalability of starks. So if we kind of zoom in on the size estimate for snarks and for starks, for starks, we can see how the size estimate for one transaction is 45 kilobytes. And then that increases as you add more transactions. Whereas for snarks, the size estimate stays constant, regardless of one transaction or 10,000 transactions. That seems like the snarks, because they aren't increasing the size as you scale the transactions, they're actually more scalable than starks. But starks are the ones with scalable at the beginning of their name. So why are starks considered scalable despite the increase in size over the amount of transactions?
That's a good question for the marketing team at Starkware, probably, or the authors of the Stark paper. I think, look, to be fair to them, I think scalable I think what they're trying to communicate by scalable means that as you have a bigger statement to prove, the proof time is better than snarks, right? So in that sense, you could say it's more scalable. I think that assumes that the proof time is the bottleneck, which I spent most of this presentation trying to explain to everyone that's actually not in the context of Web3, right? But I think you hit the nail on the head. Like snarks, the Gros16 style snarks, Plonk, Marlin, all have constant proof sizes, which is really nice because especially if you look at just the size of one transaction. Like you think about blockchains, like an Ethereum block, we're talking maybe a megabyte, a couple megabytes, right? 45 kilobytes is large, right? Like this is, you talk about, even a batch of a bunch of transactions, you're talking 100 kilobytes. That's a 20th maybe of a whole block, probably a 10th, right? If you're talking about a normal size block. And so, this is a big problem unless you decide to expand the size of each block, which of course has different scalability implications for the network and security implications.
Got it. Okay. And okay, so my second question, maybe we could play Mythbusters here, because one of the primary value propositions I was told about zk technology relative to optimistic technology was that it scales with the amount of transactions. And I don't know so I was told that as a Merkle tree grows, it's easier to prove the validity of transactions. So gas costs actually go down as there's more throughput. Is that a myth, or how does that work?
Gas costs, well, I guess it kind of depends. This is by the way, this is a totally fair question. And it's very difficult to parse this in the Twitter sphere, right? Because everybody has an approach that they've chosen. By the way, I work at Aleo. We have our own approach we haven't talked about here, but whatever, right? Everyone has their angle, right? I think what you're describing is on average, fees might be lower for an individual user if there are a lot of transactions, right? If there's because this is a single cost paid once, right? So whenever you want to do a proof verification on StarkNet, let's say it's $75. And please, like I said, no one hold me to this number today. This was pulled from some date in September. Maybe it's different. Maybe it's $50. Maybe it's 100. I don't know. Whatever. But $75 is the cost on chain, right? And so if me and you and 10,000 other people are batched into that proof, then the cost per each of us is low, right? But this cost here is constant for whoever is the rollup operator, right? And so, maybe the rollup operator is okay to subsidize the cost and lose money. But I'm saying from a rational economic actor perspective, you're never going to pay this cost unless you have enough users collectively get you to the threshold of $75 or $37, whatever it may be. So I think that's probably the clarification, is that it's cheaper on a per user basis than the Ethereum L1 potentially. But again, your trade-off is time, right? If you're willing to wait enough time for 10,000 people to do a transfer, then it's cheaper. But that's not the same as I can send you USDC right now on the main chain and pay, I don't know, maybe $10 of fees or $5 of fees, but it's right now, right? For a payments use case, I actually think that's pretty important, right? You're not going to give me the coffee unless I pay you right now.
Got it. Okay. And quick tangent relative to optimistic rollups, which we didn't touch on really at all today. Do those also scale cost of transactions linearly constant? Is it still a constant price per proof onto the main chain for optimistic rollups?
Yeah, so we didn't talk about it, and I'm candidly less of an expert on optimistic constructions than zk, but I do know a fair amount. My understanding is that, like, look, fundamentally, it's the same thing, right? You're doing the same thing in either case, right? Now, what are you not doing at the optimistic rollup? You're not doing this proof, right? You have a separate process for basically verifying that the off-chain network was doing the computation correctly, right? And that process involves, like, me checking you after the fact and being like, hey, show me this. Like, let me just double check and make sure you did this line correctly, or this line correctly, this line correctly. And so on a cost per transaction basis, like, optimistic rollups are going to win every time because of this proof verification thing doesn't exist. Now, what's the trade-off there? Well, the settlement time for optimistic rollups, I think Arbitrum has a 7-day settlement window, right? So you actually, I mean, if you just assume that you never leave optimism, it maybe doesn't matter. But assuming that you do want to go back to Ethereum and you want that to settle on the main chain, that's 7 days that you're waiting instead of 7 hours that you're waiting, right? So 7 hours is already a long time. 7 days is an even longer time. That's the trade-off. So basically what optimistic rollups are doing is just pulling you further out on this time scale at maybe a lower cost per transaction, right? But the trade-off is the time, because you need to give the verifiers time to catch any misbehaving operators.
Understood. I think the dilemma between speed and cost is very clear between optimistic and zk rollups. I want to hone in on one more question. I think Andy may have questions as well. Could you go to the comparison between zkSync and StarkNet one more time? So here, we don't see the trade-off between speed and cost, because zkSync both is cheaper to transact and quicker to transact. So what is the trade-off that zkSync is giving up and StarkNet is handling in order to sacrifice the speed and the cost? Are they improving on another angle? Is it security, or is there a missing trade-off here?
It's important to note, because it's a great question. It's important to note that, like, strictly speaking, this comparison here isn't exactly apples to apples. Now, why do I say that? Is because I took the average over the course of a month, right? And I think, remember, there's both proof verification costs and call data costs, right? And so potentially the more people that use zkSync, like, you're still having to pay a little bit more in terms of call data. If you're just talking about, strictly speaking, gas costs, and by the way, there's a great, I'll find it for you. I'll send you guys the link, but there's a great article on Medium that describes just the gas costs alone for zkSync over StarkNet. It's about 1/5 of just the gas cost for the proof verification. This additional cost here, there's probably some nuances around the number of users. Maybe the architecture is slightly different. So it's not, I want to make sure to be careful here. Like, this isn't exactly an apples to apples comparison, but I think what it highlights is, there's basically a relationship between the proof verification cost and the settlement time, as well as the fact that snarks relative to starks, going back here, like, the proof verification can be constant. So the more transactions you're packing into a stark, the more expensive it gets to verify, in fact, right? Or and vice versa if there's less, right? So it's kind of just really illustrating that instead of being a strict apples to apples comparison there. I hope that wasn't confusing.
Yeah, no, I think it answers the question, because there's a direct relationship between verification cost and verification settlement time.
Yeah, that's right. And I think the one thing to note is, again, like, the place that Starks beat Snarks very clearly is on the proof time, right? By the way, this is why certain zk EVM constructions actually use both. Polygon's approach, I think it's Polygon, I think it's just their zk, I think it's just called zkVM. They use a Stark to prove basically all the rollup transitions, and then they use a Snark to prove the verification of that Stark proof. So it's kind of like an onion, right? You have, like, a Stark proof wrapped in a Snark proof, so you get a faster prover and a constant size, verification time and proof size. What's the trade-off? Well, now you're doing 2 proofs instead of 1, right? So again, this is why hopefully the takeaway for this talk is not, I definitely did not want anyone to walk away from this being like Starks are better, Snarks are better, bulletproofs are better. The reality is these things are different on the dimensions I highlighted, and it really depends on the use case, right? In a world in which, like, for example, everyone is just building directly on Cairo on Starknet, they don't care about settling to the L1. Guess what? Proving time actually does matter more than verifying time there, because there you don't care, right? You're not settling, so the verification doesn't really matter as much, right? But if you are building a rollup construction and you're using for like payments, a long settlement time is bad because, again, the verification time is large, and therefore, no one's going to settle until there's enough money in the pot effectively to make it worth it, right? So it just all depends on the setting and the use cases. I think I would like people to take away from this.
Got it. And I think that's what I'm learning, and we're all learning as we kind of like understand and embrace this world where there's thousands of rollups that we anticipate will come online. It's like not one of them is going to win over the other. It's not a competitive landscape. They're all unique for individual use cases. Some of them use snarks. There's reasons why that makes sense for certain use cases. There are other proving mechanisms and other verifying mechanisms that make sense for other use cases. And in this world where there's thousands and thousands of rollups, each one of those makes sense. And there's a different combination of proving and verification mechanisms with multiple design trade-offs that will unveil for certain reasons that make that specific settlement proving verification combination the most applicable to the use cases that it ultimately applies to.
100%. I think it's absolutely the way to think about it is not from like a lot of us in crypto, by the way, I'm as guilty of this as everyone else, but we often think about building infrastructure from the ground up to support applications that will eventually touch a user, right? But the reality is, like, as soon as there's a killer app in crypto, by that I mean like something like everybody's checking on a daily basis, like they do a social media website, like that's going to introduce a huge demand of a specific character, and everybody on the infrastructure side is going to build tailored to that demand. So it may just turn out that the killer app is like, I don't know, like gaming or something, right? And again, as I said, maybe the people who play games don't care about permissionlessness. I kind of think that invalidates the point of blockchains, but leaving that aside for a second, maybe they just don't care. That means that you can just throw out all of the permissionlessness piece. It means that like constructions like Polygon, where it's kind of, or like a Binance chain, are kind of make sense in that world, right? Because you're like, okay, there's like 2 nodes, it's good enough, but they can go way faster, right? And that's like, does it make sense? I mean, it's hard. You can just get into philosophical arguments with people about whether or not it makes sense, unless there's an application that people clearly want. So I think you hit the nail on the head. These rollups are going to be application specific, I think, in the long term. That said, I think it is important to note that there can't be thousands of rollups, I don't think. Why is that the case? Because Ethereum has a gas limit of 30 billion per block. This Starknet proof here takes 1/6 of a block's worth of gas. So if there were 5 Starknets settling every 7 hours, then that block every 7 hours would just only be Starknet, right? And so to the extent you imagine more people using this, they want settlement more frequently, whatever, like you can see how this starts to fill things up really quickly. This is why, by the way, a lot of interest has gone into making call data cheaper and looking at off-chain, what are called data availability solutions, where you don't have to publish to the blockchain itself, right? And that in that world, assuming those exist, you could scale up to much larger numbers of rollups. Again, though, the question is, what are the assumptions, right? Because if you have like data availability over here, and you have a blockchain over here, and you have a rollup over here, at some point, you kind of lose what I think makes a blockchain special, which is trustlessness and permissionlessness. Now, again, as I just said, those applications, like what applications those enable, I have a list of several, but I think people, the market, the world is just going to have to decide whether or not those are valuable.
Yeah. There's still this open landscape in my mind of multiple Starknets. Let's say there's 7, 8 Starknets out there. There's 10 other rollups out there, and they're all publishing to the L1. Yeah, that'll fill up the block, but like Ethereum can handle it. It'll just push gas way, way up. Users are still transacting in this relatively low cost execution environment. And if there's enough transactions and the cost to publish on the L1 is split across enough users, then they still have affordable transactions. But it means the gas price on Ethereum is way, way up. There's lots of ETH getting burned, and ETH, the asset, is very bullish.
And so there's a lot of, I love this topic because there's so many variables, right? So on that, and the way you framed it, which I think is a perfectly valid potential outcome, I think it could definitely happen. And the way you framed it, though, that's very bullish for ETH, right? A lot of fees are being burned, right? But, if you're a token holder for some L2, like, what does that imply for you potentially? If there's thousands of rollups, right? Like, if one is cheaper than the other and they're all the same, I just switch, right? So it kind of like, it's kind of funny because that story implies a strong ETH tokens price story, but a weak L2 rollup token price story. Whereas you can imagine a different world where there's like one dominant L2, right? That just can handle everything and everyone just converges on it, right? Then that dominant L2 maybe can settle to like multiple chains or has a different data availability solution or something like that, right? And then ETH actually, like, you kind of might be less bullish on ETH, but you'd be really bullish on that one L2 token, right? This is why I actually don't like framing things as L1s and L2s, because in that world where, like, let's just say Optimism handles 90% of all the transactions, is it the L1 or the L2? You know what I mean? Like, it's kind of, it's like we think of it in terms of these layers, but it's actually not really right if you think about it in that world. So it's a fascinating topic, and there's many I hope you can see there's many variables at play here. Some are self-reinforcing, some are counter to each other. It's just kind of hard to know exactly what is bullish or not bullish for Ethereum or any particular L2 or a rollup approach.
That's fun to think about. If Optimism is selling all the transactions, they're the main settlement engine. So therefore they're the L1. It's like whoever is settling the most transactions ultimately is like the most based. And then whoever's got the most order flow is like, they're the execution environment.
Basically, right? And it just really comes down to like this fact that we like trustless and permissionlessness is kind of like, it's sort of like a social concept, right? Like these are social, decentralization is a social concept. And that's why like it's doesn't have a, you can consider these things in different angles because there's not like a rigorous technical definition.
Yeah, we'll see how this landscape evolves with regards to demand for settlement. And yeah. Well, Alex, it was an absolute pleasure having you on. I'm sure we could continue this in so many different directions, and hopefully we do get another chance to continue the conversation. Is there any closing thoughts on your end that you'd like to share before we roll it up?
Yeah, I guess I'll just quickly say one thing about like, okay, just, I haven't talked about Aleo at all this talk, but just, quickly, like all of this economic considerations and, is why we decided to build Aleo as a separate layer one. So it's like separate L1 smart contract platform that uses zk. A, because it's very expensive to do on Ethereum, as I hope I've convinced you guys, there's a lot of considerations. B, there's also not, we kind of glossed over this in the talk, but zk implies zero knowledge, right? Which implies privacy for use cases like identity, for example. Like identity, I think, could be a killer use case for Web3 in a way that connects Web3 and Web2. You can imagine like a different form of authentication that uses your passport in a trustless way where you just generate a proof about your age, about your citizenship, about whatever, right? And that kind of can't work in the model of a transparent blockchain because you're basically just putting your passport up on like a bulletin board for everyone to look at. But you kind of need privacy for that use case. That's why we kind of built Aleo the way we built. So I think there's a whole separate topic of people that I would ask people to consider is like, in light of the use cases that we think might be important, how important is privacy for different use cases, right? And to the extent we think it is, then the zero knowledge property of zkRollups, I think it's implied but doesn't exist, right? It becomes more important, right? And that's another dimension that we have to consider. But overall, I really appreciate you guys allowing me to share with your community here. I hope everyone benefited from this talk and got a lot out of both the presentation and the discussion. And look forward to continuing the conversation. I guess maybe people can find me on Twitter, Pruden08. That's my handle. And look forward to continuing the conversation there or at the next crypto conference with whoever maybe has listened to this. So thank you very much.
Thanks, Alex.